Part 3. In this part, you will hear 3 talks or lectures. The talks or lectures will not be repeated. There are 5 questions for each talk or lecture. For each question, choose the right answer, A, B, C, or D. Questions 21 to 25 refer to the following lecture. Listen to a talk in an art class. The instructor is talking about pigments. Whether you're working with oil, tempera, or watercolor, it's the pigment that gives the paint its color. A pigment can either be mixed with another material or applied over its surface in a thin layer. When a pigment is mixed or ground in a liquid vehicle to form paint, it does not dissolve but remains suspended in the liquid. A paint pigment should be a smooth, finely divided powder. It should withstand the action of sunlight without changing color. A pigment should not exert a harmful chemical reaction upon the medium or upon other color pigments it is mixed with. Generally, pigments are classified according to their origin, either natural or synthetic. Natural inorganic pigments, also known as mineral pigments, include the native earths, such as ochre, yellow iron oxide, and raw umber, brown iron oxide. Natural organic pigments come from vegetable and animal sources. Some examples are indigo, from the indigo plant, and Tyrian purple, the imperial purple the Romans prepared from a shellfish native to the Mediterranean. Today, many pigments are synthetic varieties of traditional inorganic and organic pigments. Synthetic organic pigments provide colors of unmatched intensity and tinting strength. The synthetic counterparts of the yellow and red earths are more brilliant and, if well prepared, are superior in all other respects to the native products. Inorganic synthetic colors, made with the aid of a strong heat, are generally the most permanent for all used. In contrast, pigments from natural sources are less permanent than the average synthetic color. Questions 26 to 30 refer to the following professor's talk. Listen to a talk in an earth science class. The professor is talking about the tsunami. The term tidal wave is often inaccurately used for a tsunami. Tsunamis have nothing to do with the action of tides. A more accurate term is seismic sea wave. There has to be a disturbance of the Earth's crust to produce a tsunami. Large earthquakes with epicenters under or near the ocean are the cause of most tsunamis. Volcanic eruptions and undersea landslides are also responsible, but less accompanied by movements of the ocean floor. Their effects are usually localized. Possibly that was true about the eruption of Krakatoa in 1883. A tsunami was responsible for most of the deaths caused by Krakatoa, yet this tsunami did not sink any ships. It did wash away several coastal villages and killed more than 36,000 people. Tsunamis work in complex ways. Some pounce on coastal settlements like large breakers. Others produce a gentle wave that floats buildings off their foundations. But then, a violent backwash may sweep buildings and people out to the sea. The tsunami that wrecked Hilo, Hawaii in 1946 was so forceful it folded parking meters. It caused needless deaths when people returned to save their belongings and got caught between waves. The deeper the water, the lower the tsunamis and the faster it moves. In the open ocean, it travels about 700 kilometers per hour, but being sometimes no more than a meter in height. A a tsunami often passes a ship unnoticed. This is what happened in 1896 during a catastrophic tsunami in Japan, which was the result of an undersea earthquake. Thousands of people were drowned on shore, while fishermen out at sea didn't notice the waves passing beneath their boats. But when they went home, they found their villages destroyed. Questions 27 to 35 refer to the following lecture. Listen to a lecture in a science class. The professor is talking about 3 Mile Island. Today, I'll be talking about an accident at a nuclear power plant. The accident I'll be discussing is the one that occurred in 3 Mile Island in 1979. By the end of the lecture, you should understand what factors contributed to the accident here. You can see 3 Mile Island in this photograph. The nuclear reactor at 3 Mile Island is in the middle of a river in the state of Pennsylvania. This nuclear reactor has 2 PWRs, which means that it has 2 pressurized water reactors. The problem that occurred in 1979 was in the number 2 pressurized water reactor. Now, we're going to discuss what happened in the number 2 reactor at 3 Mile Island. The important thing to understand about the accident was that there was a series of problems rather than a single problem. The series of problems occurred in the water cooling system. The initial problem was that a cooling system valve stuck open and the cooling water ran out. Unfortunately, the problem did not end with the cooling valve stuck open because operators misinterpreted the instrument readings. They knew there was a problem. They thought the cooling system had too much water rather than too little. Because they thought that there was too much water, they shut off the emergency cooling water. As a result, there was no water to cool the nuclear reactor. There wasn't a complete nuclear meltdown when the emergency cooling water was turned off, but there was a partial nuclear meltdown. A nuclear meltdown would exist if the uranium in the fuel core melted completely. In this situation, heat built up in the fuel core until the uranium began to melt, but it didn't melt down completely. I hope you can understand the series of events that led to the problem at 3 Mile Island. It all started with a stuck valve in the cooling system and was exacerbated by the misinterpreted reading and the improper shutdown of the emergency cooling system. Fortunately, the meltdown did not occur and was only partial and not complete.